Okay, section 6.4 is titled Logarithmic Functions, and coming off of section 6.3 we talked about exponential functions, and as I mentioned then, we were going to be looking at two types of functions in this chapter. One's exponential, one's logarithmic, and so I'm going to get into the logarithmic function here in this section. Maybe something you may not have really worked with a lot. You know, we don't typically use logarithms for much day-to-day math, but nevertheless we're going to cover them here and take a look at what we're dealing with. So logarithmic functions. Now if you'll think back to section 6.2, we talked about inverse functions, and that idea of inverse functions kind of leads us into talking about exponential and logarithmic functions, because if we take the inverse of an exponential function, we get what's called a logarithmic function. And that's exactly what these first notes are kicking off talking about here. It's saying that if you've got a one-to-one function, y equals f of x, then you can have an inverse, x equals f of y. And so we can take an inverse of a one-to-one function, and we're talking in particular here about the exponential function, you know, y equals a to the x that we just talked about. If we switch the variables around, the implicit definition is x equals a to the y. And so again, that idea of taking the inverse, you just switch the x and y values, switch the variables around, x equals a to the y. That is it's a logarithmic function. Now the problem with x equals a to the y, again I mentioned it's the implicit definition, and really what that means, an implicit definition of a function means it's not solved for y. Okay. And so the first thing we need to do is figure out, all right, if x equals a to the y, I mean that is a logarithmic function. Okay. How do we define that explicitly? How do we solve that for y? And so let's look at this next definition here. It says the logarithmic function to the base a is greater than 0, a is not 1. Sounds like the same as a exponential base, right? A is greater than 0, a is not 1. We denote that as y equals log base a of x, or y is the logarithm to the base a of x. And what that notation means, y equals log base a of x, that's true if and only if x equals a to the y. And so what this shows us, this piece right here, really what that says is if we have an exponential function, x equals a to the y, we can rewrite it as a logarithm, y equals log base a of x. Okay. And so, for example, what does that actually look like with some numbers? So if we write y equals log base 3 of x, okay, well, that means that x equals 3 to the y. Okay, so those are equivalent. Okay, and the key here, if you'll notice the base here, we say log base 3 matches the base of the exponent, right? That's you know, you just really have to figure out where the numbers are going. The base of the logarithm is the base of your exponent. And then if you'll notice, this says y equals, well, if we're switching the variables around, then over here x needs to say x equals. Okay, so y equals here, x equals here. All right, so what does that actually mean if we say y equals log base 3 of x? Well, the equivalent statements here, 4 equals log base 3 of 81 is equivalent to 81 equals 3 to the 4th. Okay, so these two are equivalent, saying the same thing. And so what's weird about this is if I were to say what is log base 3 of 81, you know, what is log base 3 of 81? Okay, that question doesn't really help us out much. You know, that's kind of a weird thing. If you were to walk up to somebody on the street and say, what's log base 3 of 81, they'd probably look at you like, they didn't know what you were talking about, because that's not something that really means anything to us, right? Log base 3 of 81. So the question that makes this statement log base 3, what is log base 3 of 81, makes sense. That's the same as asking 3 to what power is 81? Okay, now if I were to ask you that question, 3 to what power is 81, you could probably come up with an answer to that, right? You'd say, well, okay, let me see, 3 squared is 9, 3 cubed is 27, 3 to the 4th is 81, right? So hey, 3 to the 4th power is 81, so 3 to what power is 81? 3 to the 4th. Okay, notice over here, log base 3 of 81 is 4. The answer to a logarithm is an exponent. Okay, and if you can get that thought, that a logarithm, if you evaluate a logarithm, the answer is the exponent, then you can go a long way towards understanding what a logarithm is. Okay, so when you see log base 3 of 81, you're wondering what that is. Think to yourself, okay, the base of the exponent is 3. To what power gives us 81? And so the answer there is 4. If I were to just quickly here say, what's log base 2 of 4? Okay, 2 to what power is 4? 2 to the 2nd power, right? So log base 2 of 4 is 2. And so that's how these logarithms work. Okay, this question right here unlocks it, makes it make sense. So y equals log base 5 of x means that x equals 5 to the y. And we could say that negative 1 is log base 5 of 1/5. That's equivalent to 1/5 equals 5 to the negative 1. Okay, and again, you think about this piece right here. 5 to what power is 1/5? Well, you need to take a reciprocal, right? So you get that negative 1 power, okay, to get that 1/5. So that's what we're dealing with here, logarithms. So let's continue on here. It says to change each exponential expression into an equivalent expression involving a logarithm. So we want to rewrite these exponential expressions as logarithmic expressions. So 1.2 to the 3rd power equals m. We could rewrite this, and again, one easy way to do this is you could say, all right, since it equals m, it needs to equal the exponent. Okay, so kind of what is the exponent here comes down and becomes 3 equals, and then log base what? What's the base of this exponent? It's 1.2, and then the only value left there that we haven't used is m. There it is. 3 equals log base 1.2 of m. Over here, e to the b power equals 9. Now remember, e, that's that exponential value, right? We talked about that in the last section. So we could say b equals log base what? What's the base here? It's e of 9. That's the only number we haven't used there. Now for this base e logarithm, there's actually a different way we write that. Really the way you're going to see that written is with an ln, and you may remember on your calculator, I mentioned in the last section, an ln button. It's right there. That's what we call a natural logarithm. We're going to get into that here in just a little bit, but just know that for these log base e logarithms, you won't actually see log base e. We write that as an ln. The implied base there is an exponential base e. And then the last one here, a to the 4th equals 24. So we're going to say that 4 equals log base a of 24. And there it is. Now let's go the other way. This says change the logarithmic expression into an expression involving an exponent. So we're going the other direction. We've got a logarithm, we want an exponent. And so the easiest way to do these is to say, all right, log base a of 4 is 5. Base a means the exponent has the base of a. The answer to a logarithm, we said earlier, is an exponent, right? Logarithms equal exponents. Log base a of 4 equals 5 means that 5 is the exponent. So a to the 5th equals 4. Could be our answer there. Here, log base e of b equals negative 3. E is the base. Negative 3 is the exponent, equals b. That equals a little better here. And then log base 5 of 5 equals c. We could write that as 5 to the c power equals 5. And there we go. Evaluating logarithmic expressions. So we want to evaluate these. We want to work them out and come up with a number. And it says to do it without a calculator, which I think we can do. If you remember that question that we asked earlier, when we see log base 2 of 16, we can do this a couple ways. Okay, looking back up here at the instructions, we can do this a couple ways. One way is to do like we said earlier, and say, all right, log base 2 of 16 means 2 to what power is 16, right? Okay, 2 to what power is 16? If you go to your calculator, you can say 2 to the 4th power and get 16, right? So log base 2 of 16, that's going to equal 4. Alright, so that's one way to do it, is to use that question. Okay, another way is to use this up here and use what we learned in the last section about solving exponential equations. So here's an alternate method of working this same problem. We've got log base 2 of 16. We don't know what it equals though. We're trying to solve and evaluate that to find out what it equals. So log base 2 of 16 equals something. Call it x. Well, we can rewrite that as an exponential expression. 2 to the x equals 16. And notice the kind of the connection between this question and that expression we just got, right? Those kind of tie together. And then here we can rewrite 16 as 2 to the 4th power. And then sure enough, the bases match, so x is 4. So log base 2 of 16 is 4. So that's another way we can do it, using the exponential notation and what we learned in the last chapter there, or the last section. Alright, next one here, log base 3 of 1 over 27. So let's look at this like we just did, using the exponential expression. Log base 3 of 1 over 27 equals x. We can rewrite that as 3 to the x equals 1 over 27. And again, the key to this is we want both sides to be powers of the same base. So the left side is pretty much as good as it's going to get. On the right side, 27 is 3 cubed, right? So we can do that, and then we could say we're pretty close. We just need to flip this around and make that 3 to the negative 3rd power. And so now we can say, all right, both sides are powers of 3, so x equals negative 3. So log base 3 of 1 over 27 is negative 3. And there it is.